Yes, I come from a software engineering background and I did my bachelor thesis in this project together with Helena, Linda, Ali and Miroslav. So we investigated the feasibility of performing real-time analysis of time series data during CEA, carotid endarterectomy procedures. So outline of the presentation is not so bright, but go with me. So I'll go through background first of all, and I will present the types of strokes. Then I will go on with Sahlgrenska's research, the research papers we received from Helena, Linda and their group. And then I will present our product, which is called StrokeSax. And then I will present the evaluation that we did together with a research team of specialists in anesthesiology and the doctors at Sahlgrenska, and some suggestions about future work, and then a summary. I'll keep this talk brief, but yet informative. So yes, we can start off with some background. So stroke can be classified into two major types. One is hemorrhagic stroke, which occurs if there's a burst in a vessel and the bleeding leads to a stroke. The other one is cerebral ischemia, is that one we have focused on in this project, and it's when there's a clot or plaque in the vein, maybe in the carotid artery that supplies blood to the brain. And as we know, if we don't receive oxygen, it can become an acute brain injury and result in a stroke. So 2022, stroke was the second most common cause of death in the world, and if you look at death and disabilities combined, it was the third as well. And we had 27,000 reported cases in Sweden, where 25% of the reported patients, they died within 28 days, so within a month, unfortunately. And time is a very crucial factor, as Miroslav spoke about it, that they have 11 minutes to set up all the things when a patient arrives. So even seconds matter. Even if you survive a stroke, you can get lifelong disabilities and like paralysis, etc. And in the worst case, it can result in mortality. So carotid endarterectomy, for those maybe who are not aware of it, it's a surgical removal of plaque, as you see there. So there's a plaque in the carotid artery. So the doctors clamp the vein very precisely, and with this instrument they remove this plaque. And during this process, they have a tube to temporarily reroute the blood flow, and this event is called clamping. And this is a very critical one, because if you reroute the blood flow and you don't inadequate blood flow to the brain, it can result in a acute failure, and which is called cerebral ischemia. So yes, we've looked at patient data who are ongoing this procedure. So the research at Sahlgrenska, until we came into the picture, they had analyzed how to analyze non-invasive patient signals, which means that you can analyze those signals without inserting anything into the body. And they extract the signals from this mobile monitor that Miroslav spoke about, and they've only done static comparisons until now. And this is a schematic CSV file that we received from them. So we received many CSV files with lots of signals, and we focused on nearest right, nearest left, HRV and EEG signals. So I'll go through it briefly. So near infrared spectroscopy, it measures the brain activity at the right and left hemisphere of the brain, and it approximates the oxygen ratio between oxygenated and deoxygenated hemoglobin. So as we can see here, it's a healthy patient. You can see this curve, it's going quite nice. And here you see this fall in saturation. And here it was a patient that developed a stroke. And the EEG signals have 4 frequency bands, and it's dependent on the consciousness of the individual that is getting monitored. So as you see, this is a good one, a healthy patient. This is during concentration, when one is concentrated, and you can see deviations if you're depending on age. So, and this shows if the patient is conscious or not. This is during sleep. So during an operation, you can see it like this. And then we have HRV that we spoke about, that they did their study on. It measures the variability in time between each heartbreak, known as RR intervals. So it can show if the autonomic nervous system is stressed or relaxed. And as we see here, this one is a healthy patient, and this one developed a stroke. It's not always so clear like in this picture, as Miroslav said, but this one is more of a clear one. There you can see the spikes, and yeah, it resulted in a stroke, unfortunately. So indication of next step. They did their analysis and their study amongst 55 patients, and they used machine learning in a static environment. And their suggestion of next step was that they want to perform this in real time. So here is where we came into this project, me and my group. Our purpose of the project was to develop a system that can perform real-time analysis and show them as graphs in a web application. And we both wanted to do an inter-patient comparison as well as intra-patient comparisons. So we developed stroke stacks. This is the architecture of stroke stacks. We did the front end in TypeScript and React, which is very good for modular design and reusable code. I won't go into so much detail of that. We did our backend in Python because we had code bases and repositories that already was written in Python, so it was a obvious choice for us. And then we constructed a database as well, because it was not optimal to have patient files in CSV, so we did a database. So yeah, I will show you a brief demo of the application. So here, as you see, you can select the patient and the signals you want to see. Let's say we select nearest right and nearest left. Then you can compare the same signal. You can compare two signals from the same patient. You can interact with the signal, and you can see how long the monitoring has went. You can select from the drop down again. You can take two patients and get a similarity score. So this is a bi-directional similarity score. So it both shows how much patient 6 is similar to patient 7, as well as how similar patient 7 is to patient 6. And then you can select quite more signals. You can scroll down and interact with the graphs. And what you see, just a second, what you see here in purple and green is a total match. So if you select multiple signals, it will give you a total similarity score, which you can weight as well. And this is how it looks when a patient is monitored live. So if you have sensors on a patient and you get live data from the patient, you can see it's not so clear, it's not so bright. But after the monitoring, you can save this patient into the database we created and use it as a reference patient for the next comparison as well. So we did the analysis of the system together with Sahlgrenska's researchers and professionals in anesthesiology. We asked them why, how, and what. So we showed them patient graphs. We asked them, do you find this similar or do you find this not to be similar? Why? And what can you see out of a medical relevance? Because our algorithms just do a computational thing. So they had to answer 16 questions and grade them on a Likert scale. And depending, Likert scale from 1 to 5, depending on the character of the question, it can mean different things. And what we came to know is reality is not always rational. So we as engineers, we follow conventions and we think that everything will be logical. But when we met the doctors, we got to know that no, they're not to a total consensus either on what's similar or not similar. So feedback from the doctors, they find it extremely relevant to do this thing, do these comparisons in real-time environment and use algorithms. They found our system to be very responsive and adjusted to their environment, which is very hectic. Aesthetics were good. They wish to have a hybrid version because now when you connect our system, it's a router, it's multiple wires, and etc. So they want to have it more like a mobile application as well as an application on their computers because they have more patient parameters there so they can compare. And they want us to include patient demographics. I will come to that later. So we used 3 different algorithms, SimStax, Pearson correlation, and DTweave. they complement each other quite well. So I'll tell you how this SimSax works. So it's from Sax series, and what you do is that you have a graph, you divide it into piecewise aggregations like this. These boxes here, they're called bins, and you normalize all the data points. You Z normalize them first, so you get the normal distribution like here, and then you check for each bin in which quantile it appears to be, and then you assign a letter to it. This specific formation received the Sax word BAA, BCC, BC, which is this specific formation. So when you search for anomalies in other patients' graphs, you look for how many times this sequence appears there. Then you have Pearson correlation. It's a covariance, so it looks at the correlation in two variables. It requires the time series to be totally equal. It measures every data points and looks for correlation. What happens if one variable increases or decreases? What happens with the other one? So it can be a positive correlation, negative correlation, or no correlation at all. It can be plateau. So you see this table here, which indicates how strong the correlation is and where the trend is going. The last one we had was dynamic time warping. It warps it's not in the picture, but it warps a path between the data points. It doesn't require the time series to be totally equal. You can have one time series of length m and another time series of length n, and it will create a matrix like here. It's not so apparent, but yeah, it will create a matrix and it will look for the shortest path. So I will show you Euclidean distance first. If you see the Euclidean distance, it only maps straight lines, so it maps point to point. But dynamic time warping, it minimizes the distance, so it can map a point that previously had been mapped if the cost is less. So the doctor's judgment, this is ABP mean signal. The doctors gave it 4.5. They find it to be quite similar, the initial reaction here in both. And this thing over here, they say that this is an artifact and it's occurring due to a high pressure flushing. And our algorithms are not domain smart, so they don't know anything about this, but the doctor said, yeah, this is a high pressure flushing, so we don't have to count this one, so they're quite similar. They have same amplitudes and the last parts are same. So what did our algorithm say? So the first one, Pearson, it looks for correlation. So if you see here, when one graph moves, the other one is still. So the spikes and valleys, they appear at different times. So Pearson classifies this as no correlation at all. So you see this cross in the scatter plot. So yeah, next one, SimSax is good at matching sequences, but the Z normalization does that. It misses the plateau sequences like here, and as well as this spike and this spike is not similar according to SimSax, as they receive different sequences because of the Z normalization. And less volatile sections is hard for SimSax to find, as you see here. It misses this and this area because it's less volatile, and it's due to the Z normalization. On the other hand, DTV agreed with the doctors. It finds it quite similar because it can map all the y-axis without any difference in amplitude. So it finds zero amplitude differences and maps it quite well. It catches the end as well and the spikes. But it neglects the variance and sequences, and it's very dependent on distance. So these three algorithms, they compensate for each other, but none of them are totally perfect. So future improvements, we can implement a AI model. We can give it specific formations that it can look for in signals, because every signal is very unique. When we spoke to the doctors, they want to find certain formations in signals that means certain things off from a medical perspective. So yeah, so we can train the AI model in the future. So what we have showed is that you can do these comparisons in real-time environment. The algorithms are not perfect. There is no generic algorithm for all specific cases. But yeah, we were able to do this in real time, and it can be a very good, powerful tool for the future if you improvise it more. So yeah.